Hi, welcome to my YouTube channel. In this video, we'll visually explore the roots of polynomial equations, covering linear, quadratic, and cubic degree. We'll use graphs and tables so you can see exactly what's happening. So first, what even is a root? A root is simply a value of x, where f of x equals 0. In other words, it's the point where the graph touches or crosses the x-axis. That's it. Here's a graph. The horizontal line is the x-axis, and the vertical axis is f of x. This curve is f of x equals x squared minus 3x plus 2. Watch where it crosses the x-axis. Those are our roots. The curve hits the x-axis at x equals 1. That's a root. And again at x equals 2. Another root. Every time the graph crosses the x-axis, that's a root of the equation. We can verify algebraically. Plug in x equals 1. 1 minus 3 plus 2 equals 0. Correct. Plug in x equals 2. 4 minus 6 plus 2 equals 0. Correct. The graph and algebra always agree. Now let's go degree by degree. Starting with degree 1, linear equations. A linear equation is the simplest polynomial. Its general form is f of x equals mx plus b. First example, f of x equals 2x minus 4. Set f of x to 0. So 2x minus 4 equals 0. Add 4 to both sides. 2x equals 4. Divide by 2. X equals 2. That's our root. Look at the graph. The straight line crosses the x-axis exactly at x equals 2. One equation, one crossing, one root. The line crosses the x-axis at x equals 2. Second example, f of x equals negative x plus 3. Negative slope goes downward. Set it to 0. Negative x plus 3 equals 0. Negative x equals negative 3. So x equals 3. Still just one root. On the graph, the line goes downward but still crosses the x-axis at x equals 3. The slope changed, but we still get exactly one root. Negative slope, still one root at x equals 3. Third example, f of x equals 3x plus 6. Setting to 0. 3x plus 6 equals 0. 3x equals negative 6. So x equals negative 2. The root is on the negative side of the x-axis. The graph confirms it. The line crosses the x-axis at x equals negative 2. Even when the root is negative, it's still just one crossing. Steeper slope. Root is at x equals negative 2. Key rules for linear equations. A linear equation always has exactly one real root. No exceptions. The root is simply where the straight line crosses the x-axis. To solve, just set the equation to 0 and isolate x. X equals negative b divided by m. And here's the thing. It doesn't matter how steep or flat the line is. You will always get exactly one root. Always. All right, now things get a little more interesting. Let's move to degree 2. Quadratic equations. The general form is f of x equals ax squared plus bx plus c. That squared term changes everything. Because of that squared term, the graph is no longer a straight line. It becomes a parabola, that beautiful U-shape. And here's where it gets fun. A parabola can have 0, 1, or 2 real roots. Let's see what that actually looks like. Case 1, 2 roots. F of x equals x squared minus 5x plus 6. Look at the graph. The parabola dips down and cuts through the x-axis at 2 separate points. At x equals 2 and x equals 3. 2 roots. Case 2, 1 root. F of x equals x minus 2, all squared. This one is interesting. The parabola comes down, just barely touches the x-axis at x equals 2, and then bounces right back up. It doesn't cross. It just kisses it. That's called a repeated root. Case 3, No real roots. F of x equals x squared plus 1. Look at this. The entire parabola floats above the x-axis. It never comes down to meet it, not even close. So there are no real roots at all. The solutions exist, but they're imaginary. The graph makes this obvious instantly. Now, what if you don't want to draw the graph every time? What if you just want a quick answer? That's where the discriminant comes in. Delta equals b squared minus 4ac. This one little formula tells you everything. Let's look at the table in row 1. If there are two roots, take x squared minus 5x plus 6. Plug into the discriminant. We get negative 5 squared minus 4 times 1 times 6. That's 25 minus 24 equals 1. Delta is positive, so we get two real roots. The parabola crosses twice. In row 2, one root. Now x squared minus 4x plus 4. Discriminant, negative 4 squared minus 4 times 1 times 4. That's 16 minus 16 equals exactly 0. And when delta is 0, you get one repeated root. The parabola just grazes the x-axis and comes back up. In row 3, if there are no real roots, let's stake x squared plus 1. Discriminant will be 0 minus 4 times 1 times 1. That's negative 4. Delta is negative. And a negative discriminant means no real roots. The parabola never touches the x-axis, not once. So here's what I love about the discriminant. You don't need to graph anything. You don't need to factorize. Just calculate b squared minus 4ac, and you immediately know how many roots you're dealing with. It's a beautiful shortcut. Okay, now we get to my favorite one. Degree 3, cubic equations. General form is f of x equals ax cubed plus bx squared plus cx plus d. And the graph? It has this gorgeous S shape. It curves up, switches, curves back down. Really satisfying to look at. Here's a rule I want you to remember. Odd degree polynomials, like cubics, must cross the x-axis at least once. They have no choice. Think about it. As x goes to positive infinity, the curve shoots up. As x goes to negative infinity, it goes down. It has to cross 0 somewhere in the middle. It's inevitable. Let's see case 1, 3 roots. F of x equals x minus 1 times x minus 2 times x minus 3. Watch the graph. The S-curve wiggles and crosses the x-axis 3 separate times. At x equals 1, then 2, then 3. 3 factors, 3 roots. Exactly what you'd expect. In case 2, one real root. F of x equals x cubed plus x. This one factors as x times x squared plus 1. The x factor gives us a root at 0. That's the one real root. But x squared plus 1, that never equals 0 for any real number. So those two roots are imaginary. One real, two imaginary. In case 3, repeated root. F of x equals x squared times x minus 2. At x equals 0, look carefully. The curve touches the x-axis but doesn't go through. It bounces. That's the double root. Then at x equals 2, it crosses normally. Whenever you see that touching behavior, that's always a repeated root. Always. Let's see the cubic table now. In row 1, 3 roots. Equation x cubed minus 6, x squared plus 11x minus 6. Factors beautifully into x minus 1, times x minus 2, times x minus 3. 3 real roots. Discriminant is positive. Graph crosses the x-axis 3 times. In row 2, one real root. Equation x cubed plus x. Factors as x times x squared plus 1. One real root at 0. The other two are imaginary, hiding in the complex numbers. Discriminant is negative. Graph crosses the x-axis just once and keeps going. In row 3, repeated root. Equation x squared times x minus 2. Double root sitting at x equals 0. The graph touches there but doesn't go through. Then a clean crossing at x equals 2. discriminant equals 0. That touching behavior is your visual clue every single time. So here's the big takeaway for cubics. They always have either 1 or 3 real roots, never 0. Because remember, they're odd degree. They are mathematically forced to cross the x-axis at least once. You can count on that. All right, let's zoom out and see the big picture. The master rule is this. An n-degree polynomial has at most n real roots. Degree 1 gives you at most 1. Degree 2 gives you at most 2. Degree 3 gives you at most 3. The degree sets the ceiling. Here's the summary table. Degree 1, linear, straight line, always exactly 1 root. Odd degree, so it must cross the x-axis once. Degree 2, quadratic, parabola, can have 0, 1 or 2 roots. Even degree, so both ends go the same direction. Degree 3, cubic, S-curve, always 1 or 3 roots. Odd degree, so it always crosses at least once. And finally, here are the 3 things to always remember when you look at any graph. If the curve crosses the x-axis, those are real roots. If it touches without crossing, that's a repeated root. If it never reaches the x-axis, the roots are imaginary. The graph tells you everything. You just have to know what to look for. If you understand what we covered today, you've got a really solid foundation. The graph never lies. Where the curve meets the x-axis, that's your answer. Hope this helped. See you in the next one.